Okay, this is our video on Unit 2, Lesson 10. We're going to be looking at how to graph reciprocal functions in this lesson. We have two content standards we're going to be focusing on. The first one says that we need to create equations in two or more variables to represent relationships between quantities, and then graph equations on coordinate axes with labels and scales. And our second content standard is talking about with the translations of graphs, whether they're shifted left, right, up, or down. And so it's important that we can find the value of k given the graphs. So figure out what kind of shift it was based on looking at the picture. And then we're also going to experiment with cases and illustrate an explanation of the effects on the graph using technology. So we're also going to look at where we need to be able to understand how a shift or a translation of a function affects a graph. So that if I told you, for example, if I said f of x plus 6, what does that mean? And you should be able to know what that means without even having to look at a graph. But if we did do it on a graph, you should be able to obviously also see the effect that a plus 6 would have, or 6 times a function, or 6 times the variable, and then running the function on it, or the variable plus 6, and then running the function on it, something like that. So we should have graphed polynomial functions already in the past. In this lesson, we're going to figure out properties of reciprocal functions and then graph transformations of reciprocal functions. And a reciprocal function is probably something you don't know about. A hyperbola is probably something you don't know about. So those are going to be new terms that we're going to talk about in this lesson. Okay, so the first thing we're going to talk about what a hyperbola is. A hyperbola basically comes from the graph of the equation 1 over x. And you can manipulate this in lots of different ways, and we'll talk about those in this lesson. But basically, a hyperbola has asymptotes to it, which are places where the graph is discontinuous, it's not connected. And so you can see that this graph right here never touches the x-axis. It's going to get really close over here, and it's going to get really close way out here, but it's never going to touch these values. So this horizontal x-axis, everywhere you move along there, the y value is 0. So that right here, this is the equation, y equals 0 for that horizontal line. And you notice they also never touch this vertical line. And that vertical line is the equation x equals 0. So there's two asymptotes to a hyperbola. Intercepts would be where it crosses either the x-axis or the y-axis, and you can see in this particular one it never does, but sometimes they will. Sometimes a hyperbola will have intercepts. And not defined. The function is not defined whenever the denominator of a fraction equals 0, and we've already talked about that in Lesson 8 and Lesson 9 of this unit. So our first example, we're going to look at a fraction, and we're going to figure out the values of x for which our fraction is undefined. So this is just like what we did in the previous lesson, Lesson 8 or Lesson 9. So we need to factor the denominator. When we factor that, we're going to get x plus 8 times x plus 3. And so we know that any value that we plug in for x here or for here that makes that piece equal 0, those are going to be the values for where the function is not defined. So we can see that the function is not defined. It's undefined at -8 for this first piece, and it's undefined at 3 for the second piece. So there's two values where this function is undefined. Okay, check your progress, pause the video, and you have your answer. Go on to the next screen. And our answer this time is choice C. Okay, in example 2, we're going to look at different properties of reciprocal functions. So we need to identify the asymptotes, the domain, and the range of the function. So the asymptotes are the lines. They're imaginary lines that the function is never going to be allowed to touch. So the graph that we have is the equation 3 divided by x minus 2. And this is the picture that we can see from that graph. So the first thing we want to do is figure out what values of x make the function undefined. And obviously, if we look at the denominator, the value x equals 2 is going to make our function undefined. So that means that there's an asymptote at x equals 2. So they used a kind of weird scale on here. Their scale on this graph is every 2 blocks is 5 units. So 1 block is 2.5 units, which to me is just a really weird scale, and I don't know why they used it. But let me draw in an asymptote, this asymptote x equals 2. It's about right like there. So we can see from this that this graph is going to get really close to the number 2 over here, and it's going to get really close to 2 up here, but it's never actually going to touch 2, because if it did, this function would be undefined. So it says from x equals 2, as the x values decrease, as they get lower, the function values approach 0. If we look back at this graph, as I get smaller and smaller x values, notice how this function is getting really close to 0. And if this side over here, this is also getting really close to 0. So there's going to be another asymptote. I can draw that one in. Let me change the color. Let's do a red. There's going to be another asymptote right here along the x-axis. And that's the equation oops. Let me undo that and change back to my pen. That's the equation y equals 0. So we have the vertical line is x equals 2. That's one of our asymptotes, and our other asymptote, our horizontal asymptote, is y equals 0. And that's what this screen right here is saying. So we've looked at the two asymptotes for this problem, and then we need to talk about the domain and the range. So we're going to go back. It's got the answer right here. It says the domain is all real numbers not equal to 2, and the range is all real numbers not equal to 0. So basically, let's go back and look at the graph real quick. We're here on this graph, and if you look at it, the domain is all your x values. So you can see this function goes forever in the negative direction. It's coming along, and then it starts, there's a little bit break here. So our asymptote, there's a break. It can't be x equals 2. Once we jump past x equals 2, you can see that it goes out forever to positive infinity. So our domain is just every x value except for the asymptote value, positive 2. In our range, the y direction, you can see it goes down to negative infinity and up to positive infinity. So it's every y value except for our asymptote, which was 0. So that's how they come up with the domain and the range in the answer down here for this slide. So part B, we've got a new function. We're going to identify asymptotes, domain, and range for this function. So in order to find our asymptotes, our vertical asymptote, we need to figure out where the function is undefined. So we're looking at this x plus 2 in the denominator. So that's going to be undefined when x is negative 2. So there's an asymptote, a vertical asymptote at x equals negative 2 right here. And then we look at our horizontal asymptote, and we can see right here there's going to be a horizontal asymptote. There's some value in here. And they just say from x equals negative 2, as the x values decrease, the function values approach 1. How do you know that? Where did they come up with that? Let me show you how they did that. So they have y equals, this was our original equation from the previous slide, 1 over x plus 2 plus 1. So in order to figure out your horizontal asymptote, what you want to do is look at your fraction right here. And we're going to look at the powers of our variable. So we have a variable in the denominator that's the first power, but we don't have any variables up here. Whenever the power is larger in the denominator, this fraction is going to approach the value of 0 as you put in really big x numbers. So if I put in like a million plus 2, and I did 1 divided by 1,000,002, you're going to get a really, really small number. So this fraction gets closer and closer to 0 the farther I go out. So as this becomes 0, this equation basically becomes 0 plus 1, which is 1. That's how they get this 1 answer up here. So our asymptote is at y equals 1, or f of x equals 1. If I go in the negative direction, really, really far to the left, so close to negative infinity, a really, really large negative number, if I do 1 divided by a really, really large negative number, that's still going to be, technically it would be negative 0, but there is no such thing as negative 0, it's still just 0. So it still becomes 0 plus 1. So our asymptote on each side is just y equals 1. So again, the domain and the range is the same process as before. The domain is all real numbers not equal to -2, and the range is all real numbers not equal to 1. We're just ignoring, we're taking out the asymptote values. All right, check your progress problem. Pause the video as long as you need. When you have your answer, go on to the next screen. Here, our answer this time is choice D. We have a vertical asymptote at x equals -3 and a horizontal asymptote at f of x, or y equals 0. For part B, we've got another function, similar kind of process. Pause the video when you have your answer, go on to the next screen. This time we're just doing domain and range. Your answer to this one is choice C. We're going to pick up with the rest of the examples in another video because I'm running out of time for this one.